Long before telescopes pierced the darkness of space, humanity gazed up at the stars with nothing but their own brilliance to guide them. Picture this centuries ago, under ink-black skies untouched by city lights. Astronomers held delicate brass instruments in their hands, tools so precise they could measure the distance between stars or predict the movements of planets. These weren't just devices, they were masterpieces of art and science, forged by minds desperate to decode the universe's grandest secrets. And yet, most of their names have faded from memory, their stories buried under the march of progress. But what if I told you these forgotten instruments didn't just map the cosmos, they shaped the very foundations of astronomy? Think about the last time you looked up at the night sky, feeling that quiet awe at its vastness. Now imagine doing that without satellites, without telescopes, without any of the technology we take for granted. How would you even begin to make sense of it? That's exactly what these ancient tools were designed to solve. Take the Astrolabe, for example, a handheld marvel that could tell time, chart stars, and even navigate the open seas, all with a few careful adjustments. Or the Armillary sphere, a complex ringed model of the heavens that let astronomers visualize the celestial dance we now understand as orbits. These weren't just clever gadgets, they were the keys to unlocking mysteries that had baffled humans for millennia. What's truly astonishing is how much these instruments accomplished with so little. No electricity, no digital calculations, just pure ingenuity, patience, and an unshakable curiosity about the universe. And here's the thing, their legacy isn't just a footnote in history. The principles they pioneered still echo in modern astronomy, from the way we track satellites to how we understand the mechanics of the solar system. So why have they been overlooked? Perhaps because their stories are humbler, quieter than the flashy narratives of later discoveries. But that's about to change. Over the next minutes, we're going to resurrect these forgotten marvels, piece by piece, and by the end, you'll see the night sky not just as it is today, but as it was seen through the eyes of the past. Ready to begin, let's step into the shadows of history and meet the tools that mapped the cosmos before light ever touched a telescope's lens. The astrolabe was more than just a tool, it was a revolution in the palm of your hand. Imagine holding a device that could answer questions like when will the sun rise tomorrow, or where will Mars be next month, with just a few careful adjustments. Its design was sheer genius, a flat, circular disc etched with star maps, rotating parts to align with the heavens, and markings that acted like an ancient cosmic calculator. What made it truly extraordinary wasn't just its precision, but its universality. From the deserts of Arabia to the monasteries of Europe, this single instrument became the shared language of astronomers, navigators, and even religious scholars tracking holy days. One of its most remarkable features was its adaptability. Unlike modern gadgets locked to a single purpose, the astrolabe could be customized with different plates for different latitudes. Sailors used it to find their way across uncharted seas, while farmers relied on it to predict the best time to plant crops. Even poets and philosophers marveled at its ability to make the infinite cosmos feel tangible. The Persian astronomer Al-Biruni once wrote that mastering the astrolabe was like holding a model of the universe itself, a testament to how deeply it shaped humanity's relationship with the stars. But here's the twist, the astrolabe didn't just spread knowledge, it connected civilizations. When Islamic scholars translated and expanded on Greek texts, they didn't just preserve Ptolemy's work, they transformed it, adding new star charts and refining its mathematics. By the time it reached medieval Europe, it had become a bridge between cultures, proof that curiosity knows no borders. And while today we'd simply pull out a smartphone for the same answers, there's something hauntingly beautiful about the astrolabe's physicality. Turning its dials wasn't just about data, it was a ritual, a way of touching the sky. So the next time you check your phone for the weather, spare a thought for this ancient predecessor. It didn't just tell time or map stars, it taught us how to see the universe as something we could measure, understand, and even hold. And that's a legacy no app can replace. The Armillary sphere was like holding the entire universe in your hands, a delicate, rotating framework of rings that mirrored the movements of the heavens. Picture a series of interlocking circles, each one representing a celestial path, the ecliptic for the sun's yearly journey, the celestial equator dividing the sky, and the bands marking the wanderings of planets. Unlike the handheld astrolabe, this was a grander vision, a three-dimensional map that made the cosmos feel almost touchable. And while it might look like an intricate sculpture today, back then, it was as vital to astronomy as a telescope is to modern stargazers. What made the Armillary sphere truly remarkable was its dual role as both a teaching tool and a precision instrument. In ancient Greece, Claudius Ptolemy relied on it to demonstrate his geocentric model, showing how the sun, moon, and planets revolved around Earth in perfect, predictable circles. Centuries later, astronomers like Tycho Brahe took the concept even further, constructing massive versions with painstaking accuracy to track celestial movements down to the smallest fraction of a degree. These weren't just models, they were the supercomputers of their time, capable of predicting eclipses, solstices, and planetary alignments long before the invention of logarithms or slide rules. But the sphere's brilliance wasn't just in its mechanics. It was a bridge between cultures, appearing in strikingly similar forms across the world. Chinese astronomers crafted their own versions as early as the 4th century, using them to refine calendars and imperial rituals. In Europe, Renaissance scholars adorned their libraries with gilded armillary spheres, symbols of both intellectual prestige and a deep fascination with the cosmos. And yet, despite their shared purpose, each culture imbued these instruments with unique meaning. Some saw divine order in their perfect rings, while others used them to challenge old assumptions about the universe. Perhaps the most poetic part of the Armillary sphere's story is how it reflects humanity's endless desire to see the unseen. Without satellites or space probes, these rings and bands were the only way to visualize the celestial machinery at work. Turning one by hand wasn't just calculation, it was theater, a performance of the heavens unfolding right before your eyes. And while we've long since moved past the geocentric model it once defended, the sphere's legacy lingers. Modern celestial globes and even some planetarium projectors owe a quiet debt to this ancient invention. So the next time you look up at the stars, imagine being an astronomer 500 years ago, guiding those rings into alignment. You wouldn't just be solving equations, you'd be touching the very fabric of the sky. And in that moment, the universe wouldn't feel distant or abstract. It would turn quite literally at your fingertips. The Quadrant was the unsung hero of celestial navigation, a deceptively simple tool that turned the vast, intimidating sky into a measurable guide. Think of it as an ancient protractor for the stars, a flat, quarter-circle device with a sighting mechanism along one edge. By aligning it with a star or the sun and reading the angle marked along its curved edge, sailors and astronomers could pinpoint their position on Earth or chart the heavens above. It wasn't flashy, but it was revolutionary. While the Astrolabe and Armillary sphere captured imaginations with their intricate designs, the Quadrant did something extraordinary. It made precision accessible. For sailors, the Quadrant was nothing short of a lifeline. Imagine being on a wooden ship in the middle of the ocean, with no landmarks, no GPS, just the endless stretch of water and sky. By measuring the height of Polaris, the North Star above the horizon, a navigator could determine their latitude with surprising accuracy. It wasn't perfect, rough seas made readings tricky, and cloudy nights could leave crews stranded, but it was far better than guessing. The quadrant's reliability helped launch the age of exploration, enabling voyages that connected continents and reshaped the world. Astronomers, though, took the quadrant to another level. Tycho Brahe, the legendary Danish stargazer, built a mural quadrant, a massive version mounted on an observatory wall that could measure star positions with jaw-dropping precision. His meticulous records, made without a single telescope, were so accurate that they later helped Johannes Kepler crack the code of planetary motion. That's the quadrant's hidden brilliance. It wasn't just a tool for finding your way. It was a foundation for discovering how the universe worked. What's often overlooked is how the quadrant blurred the line between art and science. Many surviving examples are beautifully engraved, their brass surfaces decorated with zodiac signs, floral patterns, or even poetic inscriptions. This wasn't just ornamentation, it reflected a time when studying the stars was as much about wonder as it was about calculation. And while modern instruments have replaced it, the quadrant's legacy lives on. Every time a satellite uses star tracking to orient itself in space, or a telescope aligns to a distant galaxy, it's following principles this humble device helped establish centuries ago. So the next time you hear about high-tech navigation or space exploration, remember the quadrant. It proved that you don't need complexity to achieve greatness, just clarity, patience, and a willingness to look up. The Nocturnal was timekeeping stripped down to its purest form. No gears, no springs, just a simple wooden or brass disc and the unwavering stars above. Picture a medieval scholar standing in a monastery courtyard, turning the instrument's concentric rings until the pointer aligned with Polaris and the Big Dipper's pointer stars. In that moment, the rotating dial revealed the hour as clearly as any clock face, all by decoding the slow pivot of the night sky. It was a brilliant solution to an ancient problem: how to measure time when the sun was gone and mechanical clocks were rare or unreliable. What made the Nocturnal so ingenious was its elegant simplicity. Unlike the Astrolabe's intricate star maps or the quadrant's precise angles, this tool required just two reference points: Polaris, the fixed North Star, and the Big Dipper's rotation around it. By matching the date on the outer disk to the Dipper's position, users could read the hour on the inner scale. Farmers used it to gauge when to start pre-dawn chores, sailors to track watch shifts during long voyages, and monks to maintain the strict rhythms of prayer through the night. It wasn't just a tool, it was a way of syncing human life with the cosmos's silent clockwork. But the Nocturnal story also hints at a deeper truth: how much we've lost in our modern relationship with time. Today, we glance at phones or smartwatches without a second thought, utterly divorced from the celestial patterns that once dictated every aspect of life. For medieval users, checking the hour meant stepping outside, craning their necks to the stars, and feeling the Earth's rotation in their bones. The Nocturnal didn't just tell time, it connected them to the universe's grand rhythm in a way our digital displays never could. Remarkably, versions of this tool persisted well into the 18th century, a testament to its reliability. Explorers like John Davis even adapted it for navigation, proving its versatility. Yet perhaps its most enduring legacy is the way it embodies astronomy's humble origins. Before observatories and telescopes, before even the widespread use of clocks, humanity measured the night with nothing more than a disk, a star, and their own ingenuity. And in that simplicity lies a quiet challenge: to look up now and then and remember that time was never just numbers on a screen. It was written in the stars all along. The Torquetum was the Swiss Army knife of medieval astronomy, a towering, intricate masterpiece that could transform celestial coordinates with the turn of a dial. Picture a brass skeleton of interlocking rings and rulers, each tier representing a different framework for mapping the sky, the horizon, the ecliptic, the equator. Unlike simpler instruments, the Torquetum didn't just measure, it translated. Want to know a star's position in relation to the zodiac? Adjust the upper tier. Need to convert that to equatorial coordinates? Rotate the middle ring. This wasn't just a tool, it was a mechanical brain, capable of solving problems that would have required pages of handwritten calculations. What set the Torquetum apart was its sheer versatility. Arabic astronomers like Nasir al-Din al-Tusi refined its design to tackle the limitations of earlier instruments, allowing observers to switch seamlessly between celestial reference points. European scholars, particularly in the Renaissance, adopted it with awe, using it to predict planetary positions or track the sun's path through the zodiac. Its complexity was both its strength and its downfall. While it offered unmatched precision, mastering its labyrinth of adjustments required near-obsessive dedication. Surviving examples are rare today, not because they failed, but because few had the skill to wield them. Yet the Torquetum's legacy isn't just in its mechanics. It was a bridge between worlds, blending Islamic astronomical innovations with European observational traditions. When you see its spiraling tiers, you're looking at the ancestor of modern telescope mount systems that still rely on converting between coordinate systems to pinpoint celestial objects. That's the Torquetum's quiet triumph. It proved the universe could be measured in multiple languages, each revealing a new facet of its order. Now shift your gaze to a far humbler tool, the cross staff. Where the Torquetum dazzled with complexity, this device embodied raw simplicity, a wooden staff with a sliding crosspiece held up to the eye like a makeshift ruler for the sky. Yet with nothing more than aligned notches, it could measure the angular distance between stars or the height of a lighthouse on a distant shore. Mariners adored it for its rugged practicality, while astronomers like Tycho Brahe used refined versions to chart the heavens with startling accuracy. The cross-staff's secret was its adaptability. Slide the crosspiece closer and you could gauge the moon's diameter, extend it fully, and you'd capture the gap between Jupiter and its moons. It was astronomy democratized, no intricate gears, no delicate brasswork, just geometry in its purest form. And when telescopes finally arrived, it was the cross-staff's basic principle that evolved into the filler micrometer, a device still used to measure star separations. So while the Torquetum whispered of the cosmos's layered elegance, the cross-staff shouted something just as profound. That sometimes the universe yields its secrets not to complexity, but to persistence and a steady hand. The cross-staff was proof that brilliance often wears the humblest disguise, just a wooden pole with a sliding crosspiece, yet capable of measuring the vast distances between celestial bodies. Sailors called it Jacob's staff, a nod to its biblical simplicity, and it became their trusted companion on uncharted waters. Picture a 16th century navigator on the deck of a creaking ship, squinting through the crosspiece to align the horizon with Polaris. That single measurement, crude as it seemed, could reveal their latitude with enough accuracy to guide them home. But the cross-staff wasn't just for seafarers. Astronomers like Tycho Brahe used refined versions to track planetary movements, while surveyors adapted it to map land with surprising precision. Its magic lay in its adaptability. Slide the crosspiece closer for measuring the moon's diameter, extend it to span the gap between two stars, or tilt it to calculate a mountain's height from miles away. What's often overlooked is how the cross-staff embodied a radical idea, that the cosmos could be measured with nothing but geometry and patience. Unlike the ornate astrolabe or the towering torquetum, it demanded no intricate craftsmanship or mathematical expertise. A farmer could carve one from spare wood and use it to predict planting seasons by the stars' positions. That accessibility made it revolutionary, even as telescopes began dotting observatories in the 17th century. The cross-staff clung to relevance, its rugged practicality unmatched for quick measurements under open skies. Galileo himself likely used one in his early observations of Jupiter's moons, bridging the gap between medieval tools and the dawning age of optics. The cross-staff's legacy is etched into modern astronomy in ways we rarely notice. Its basic principle, using aligned markers to gauge angles, evolved into the filler micrometer, a device still used in telescopes to measure star separations. And while we've traded wooden staffs for digital sensors, the lesson remains. Sometimes the most profound truths are uncovered not by complexity, but by stripping away everything unnecessary. The cross-staff didn't just map the stars, it reminded us that the universe speaks in geometries, and all we need to do is listen. Now, let's turn to an instrument that dared to be neither simple nor grand, but something perfectly in between: the triquetram. With its 3 elegant arms and sliding markers, it offered a middle path between the cross-staff's austerity and the torquetum's complexity. Picture an astronomer in a Renaissance courtyard, adjusting the triquetram's scales to track Venus's slow dance across the zodiac. Unlike the cross-staff, which excelled at quick measurements, the triquetram was built for patient precision, its segmented rods allowing calculations of planetary latitudes that rivaled far bulkier instruments. What it lacked in portability, it made up for in versatility, earning a quiet but vital role in the history of celestial mapping. The triquetram's design was deceptively clever. 2 fixed arms formed a right angle, while a third, marked with precise gradations, slid between them like a ruler for the sky. By aligning one arm with the horizon and the other with a star, observers could read altitudes directly from the scale, no complex adjustments needed. This made it especially popular among scholars who valued accuracy but lacked the resources for elaborate setups. Even Copernicus reportedly used one in his early work, its straightforward mechanics perfectly suited to his revolutionary calculations. Yet the triquetram's greatest contribution might be how it symbolizes astronomy's enduring balance between art and utility. Its name, derived from the Latin for 3-cornered, hints at its geometric purity, while its polished wood and brass fittings reveal the care artisans poured into even the most functional tools. In a world racing toward telescopic breakthroughs, the triquetram stood as a reminder that progress isn't always about replacing the old. Sometimes it's about refining what already works. And as we'll see next, that philosophy extended far beyond the observatory, shaping instruments that mapped not just the heavens, but the very fabric of time itself. The triquetram was geometry made tangible, a 3-armed instrument so elegantly simple that even its name, derived from the Latin for 3-cornered, whispered of pure mathematical harmony. Picture it standing in a medieval observatory, 2 straight rods fixed at a right angle like a carpenter's square, with a third, carefully calibrated arm sliding between them like a bridge between earth and sky. This wasn't just a tool, it was Ptolemy's brainchild brought to life, a device he described in meticulous detail as a way to measure the moon's height or the sun's path without the fuss of more complex machinery. And while it lacked the astrolabe's artistry or the torquetum's imposing tiers, the triquetram had something far more enduring: reliability. What made it extraordinary was its adaptability. Renaissance astronomers, dusting off Ptolemy's ancient texts, realized its sliding scales could track planetary movements with surprising accuracy. Imagine Copernicus hunched over his wooden triquetrum in the dim light of a Polish tower, its arms casting long shadows as he recorded Venus's gradual shift against the stars. Each measurement was a tiny rebellion against the old geocentric order, proof that the heavens moved in ways Aristotle never imagined. The triquetrum's genius lay in its refusal to overcomplicate. It didn't need intricate gears or spinning disks to reveal celestial truths, just careful alignment and a scholar's patience. But the triquetrum's story isn't just one of precision. It's a lesson in how ideas echo across centuries. Arab astronomers refined its design, medieval Europeans adopted it, and by the 16th century, it had become a quiet staple in observatories from Krakow to Constantinople. Unlike flashier instruments, it demanded no gold leaf or ornate engravings, just polished wood and brass, worn smooth by generations of hands adjusting its arms. That humility was its strength. While the Armillary sphere dazzled patrons and the Astrolabe fit neatly into pockets, the triquetrum did the unglamorous work of grinding out data, night after night, that would eventually help topple Earth from the center of the universe. Yet perhaps its most poignant legacy is how it embodies the slow, collective nature of discovery. No single astronomer invented the triquetrum's final form. It evolved through countless iterations, each craftsman or stargazer adding a tweak, a refinement, a new way to read its scales. And when telescopes finally made it obsolete, its spirit lived on in the sextants and theodolites that still rely on its core principle, that the cosmos can be measured one careful angle at a time. Now, let's turn to an instrument that captured the entire night sky in the palm of your hand, the celestial globe. Unlike flat star charts or calculating devices, this was a miniature universe, a sphere etched with constellations so detailed you could trace Orion's belt with your fingertip. Crafted from brass or wood, these globes weren't just scientific tools. They were treasures passed down like heirlooms and studied by candlelight. To hold one was to hold the heavens themselves, frozen in time and spun to your will. The celestial globe was more than a tool. It was a universe in miniature, a shimmering sphere of brass or wood that fit snugly in your palms yet contained the entirety of the night sky. Imagine a 16th century scholar in a candlelit study, tracing the etched lines of Draco or Ursa Major with their fingertips, feeling the ridges where stars clustered like celestial cities. Unlike flat maps that distorted constellations, these globes preserved the true arrangement of the heavens, their three-dimensional curves mirroring the vault of space itself. Arab artisans elevated their construction to an art form, inlaying silver for stars and engraving intricate zodiac figures that seemed to dance across the surface. But these weren't just decorative marvels. When European explorers ventured into southern latitudes, where unfamiliar stars like the Southern Cross blazed overhead, their celestial globes became lifelines, portable atlases that could reorient them beneath alien skies. What made these globes extraordinary was their dual role as science and storytelling. Turn one slowly, and you'd see Orion's belt aligned precisely as it appears in winter, but you'd also glimpse the mythology woven into its design, the hunter's raised club, the lion's pelt draped over his arm. Tycho Brahe's collection, painstakingly crafted in his Danish observatory, included globes that plotted not just stars but comets, proof that even the heavens' unpredictability could be captured in metal. For navigators, the globes offered practical magic. By aligning the sphere with the local horizon using a built-in meridian ring, a sailor could simulate the night sky for any date or location, transforming abstract star charts into a personal guide. Yet the celestial globe's deepest legacy lies in how it bridged cultures. Persian astronomer Abd al-Rahman al-Sufi's 10th century Book of Fixed Stars described constellations with such precision that his work became the blueprint for globes from Baghdad to Barcelona. When these instruments reached Renaissance Europe, They carried not just star positions but centuries of Islamic astronomical knowledge, silently reshaping Western cosmology. Today, surviving examples in museums still gleam with that shared history, their surfaces a palimpsest of Greek, Arabic, and Latin star names, a testament to humanity's collective gaze upward. Now let's journey even further back, to the banks of the Nile, where a far simpler instrument helped raise monuments that touched the sky. The Merkhet, ancient Egypt star clock, was little more than a palm-sized notched stick with a plumb line dangling from one end. But in the hands of priest astronomers, it became a celestial ruler. Picture them standing atop a half-built pyramid at dusk, aligning the Merkhet's string with Polaris or the belt of Orion. The slightest tilt revealed true north, allowing builders to orient each massive stone with divine precision. This wasn't just surveying, it was sacred geometry, a dialogue between earth and sky that turned pharaohs' tombs into eternal compasses. What's astonishing is how the Merkhet's design echoed across millennia. Its basic principle, using a weighted line to find vertical alignment, resurfaced in medieval astrolabes and even modern theodolites. But for the Egyptians, its power went beyond engineering. Temple inscriptions describe Merkhet-wielding priests as followers of Horus, timekeepers who synchronized rituals with the stars' movements. When the pyramid's corridors aligned perfectly with Thuban, the pole star of their era, we're witnessing the Merkhet's silent legacy, proof that even the grandest human achievements begin with a humble tool and a patient eye fixed on the heavens. The Merkhet might look unassuming, just a notched stick with a dangling string, but in the hands of Egyptian astronomers, it became a cosmic compass. Picture this: on a still, moonlit night along the Nile, a priest holds the palm wood sight to his eye, waiting for the moment when the bright star Thuban aligns perfectly with the plumb line's shadow. That precise alignment, repeated over nights, would reveal true north, allowing builders to orient the Great Pyramid's massive foundation stones within a jaw-dropping 1/20th of a degree. This wasn't just navigation, it was celestial engineering where architecture mirrored the heavens. What's astonishing is how the Merkhet's simplicity belied its sophistication. Unlike later instruments with gears or lenses, this tool relied on gravity and patience. The weighted string, swaying gently in the desert breeze, had to settle into absolute vertical stillness before measurements could begin. Priests likely used pairs of merkhets, spaced apart like surveyor's stakes, to create reference lines stretching hundreds of feet across construction sites. The pyramid's near-perfect cardinal alignment, still bafflingly accurate today, stands as silent proof of their skill. But the Merkhet's purpose went beyond practicality. For the Egyptians, stars weren't just guides, they were divine pathways. Aligning temples to Thuban, then the pole star, connected pharaohs to the eternal cycle of the gods, turning stone into a gateway between earth and sky. The Merkhet's legacy stretches far beyond Giza. Similar plumb-line tools appear in cultures from Mesopotamia to Mesoamerica, each adapting the concept to their own skies and sacred sites. When medieval Islamic astronomers refined the astrolabe, they included a weighted string called a thread of reckoning, a direct descendant of the Merkhet's design. Even modern satellite arrays, calibrated to celestial coordinates, echo that ancient impulse to anchor human creations to the stars. Yet perhaps the most poignant lesson of the Merkhet isn't in its precision, but in its perspective. Today, we take north for granted. It's a digital readout on our phones, stripped of wonder. But for those Egyptian priests, finding true north was a ritual, a conversation with the cosmos. Every aligned pyramid corner whispered the same truth, that even the grandest human ambitions are just reflections of the universe's order. And in that humility lies a quiet challenge to look up now and then and remember how much we owe to a piece of string and a star's steady light. The camel was elegance carved from necessity, a wooden card no larger than a bookmark, tied to a string with carefully spaced knots. Yet in the hands of Arab navigators, this unassuming tool became a lifeline across the treacherous waters of the Indian Ocean. Picture a monsoon season night, waves battering a D-house hull as the captain stretches the camel's string between his teeth, aligning the card's lower edge with the horizon and its top with Polaris. The knot resting against his nose reveals his latitude, each one painstakingly calibrated to a specific port's position. No gears, no brass, just a sailor's muscle memory and the star's unwavering light. What made the Camel revolutionary wasn't just its precision, but its adaptability. Unlike bulkier instruments that required stable ground, this pocket-sized marvel thrived on rocking decks. Persian and Omani traders memorized knot sequences like secret codes, one for Hormuz's bustling harbor, another for Zanzibar's spice docks. The string itself told stories. Sun-bleached segments marking routes sailed 100 times, new knots added as explorers ventured farther down Africa's coast. By the time Vasco da Gama rounded the Cape of Good Hope, Arab pilots had already mapped those waters with nothing but this card and string, their knowledge woven into the camel's tactile language. The camel's brilliance lay in its duality. For illiterate sailors, the knots were a braille-like guide. For scholars, they encoded mathematical relationships between star angles and terrestrial geography. Medieval Arabic manuscripts describe its use with near-poetic reverence. One text compares stretching the string to drawing a bowshot toward heaven's dome. And when European navigators adopted the design, they unwittingly preserved a legacy that stretched back to 9th century Baghdad, where astronomers first systematized these stellar measurements. Today, that legacy lingers in every sextant's arc. The camel's core innovation, using horizon and star to fix position, evolved into the sextant's mirrored geometry. But there's poetry in how the older tool achieved similar results without mirrors or precision gears. Where a sextant calculates, the camel felt its way home, trusting the body's own measurements, arm's length, knotted string, the press of teeth against fiber. In an age of GPS, that intimacy feels almost magical, a reminder that the universe's grandest truths can sometimes be measured by something as simple as a piece of string and a sailor's steady hand. Long before telescopes cast their gaze skyward, Chinese astronomers were mapping the heavens with instruments of breathtaking precision. Take the Armillary sphere, not the European version we've discussed, but the Han Dynasty's masterpiece, its bronze rings gleaming under the imperial observatory's rafters. This wasn't just a tool, it was a cosmic engine, its interlocking circles tracking the sun's path, the moon's phases, and the wanderings of planets with a level of detail that would leave Renaissance scholars in awe. The astronomer Zhang Heng refined it further in the 2nd century, adding a water-powered mechanism that rotated the sphere automatically, a celestial clockwork centuries ahead of its time. But China's true genius lay in merging astronomy with practicality. Consider the gnomon, a simple shadow-casting pole planted in courtyard stones. By measuring the sun's shadow at noon throughout the year, scholars calculated the solar year's length with staggering accuracy, within minutes of modern measurements. These weren't abstract exercises, they shaped empires. The imperial calendar, synchronized to the gnomon's readings, dictated planting seasons, tax collections, even the timing of coronations. A misstep could mean famine or unrest, so astronomers guarded their gnomons like state secrets, etching data onto bamboo slips for generations to come. Then there was the cosmic board, a device so ingenious it blurred the line between abacus and astrolabe. Picture a lacquered wooden grid with sliding beads representing stars, their positions adjusted to predict eclipses or planetary conjunctions. It was mathematics made tactile, a far cry from Europe's brass and gear complexity, yet just as powerful. Court astronomers used these boards to warn emperors of celestial omens. A solar eclipse might signal divine displeasure, demanding rituals to restore harmony between heaven and earth. What's striking is how deeply astronomy was woven into China's cultural fabric. Eclipse records from 2,000 years ago survive on silk scrolls, their ink still vivid beside notes like, "The stars appeared at midday and the people trembled." Emperors employed entire bureaus of sky watchers, their observations guiding everything from bridge construction to military campaigns. When the Song dynasty simplified instruments for wider use, it wasn't just about efficiency. It reflected a belief that understanding the heavens wasn't reserved for elites. Even farmers consulted star charts painted on temple walls, aligning their lives with the cosmos's rhythms. Now, shift your gaze across the Pacific, where Mesoamerican cultures were making eerily similar leaps without a single bronze ring or gnomon. The Mayas' towering observatories at Chichen Itza, aligned to Venus's risings, prove that brilliance needs no shared blueprint. Their astronomers tracked celestial cycles with nothing but carved stone and naked eyes, yet their eclipse predictions rivaled China's. How two worlds, oceans apart, converged on such parallel paths is one of history's most tantalizing mysteries. The caracol at Chichen Itza stands as one of history's most ingenious fusions of architecture and astronomy, a stone observatory so precisely engineered that its very walls functioned as celestial measuring devices. Picture this: as Venus, the brilliant evening star, reaches its northernmost point in the sky, its light pours through a narrow slit in the caracol's tower, striking a marker on the opposite wall. This wasn't accidental. Every curve of its spiral staircase, every strategically placed window, was calibrated to track the movements of planets and stars with a precision that rivals modern instruments. The Maya didn't just build structures, they encoded the heavens into stone. What makes the caracol extraordinary isn't just its accuracy, but its duality. By day, it was a temple, its terraces humming with rituals. By night, it transformed into an astronomical workstation, where priests recorded Venus's cycles, information so vital it dictated warfare, agriculture, even coronations. The Maya believed Venus's appearances as the morning and evening star represented the god Kukulkan's cyclical journey through the underworld. When the planet's position aligned with the caracol sightlines, it wasn't just data, it was divinity made visible. And this marriage of science and spirituality wasn't unique. Across Mesoamerica, from the Pyramid of the Sun at Teotihuacan to the observatory at Monte Albon, buildings doubled as cosmic calendars, their staircases counting the days between solstices, their facades casting shadows that marked equinoxes like clockwork. The Mayas' astronomical prowess shines brightest in their codices, folded bark paper books filled with complex tables predicting eclipses, planetary motions, and even the cycles of Mars. One Dresden Codex page details a lunar eclipse forecast accurate to within 2 hours, calculations made centuries before Europe's telescopes. These weren't abstract equations, they were survival guides. A misplaced eclipse prediction could mean failed crops or lost battles, so astronomer priests refined their models over generations, blending observation with meticulous record-keeping. Imagine the pressure, crouched in a torchlit chamber, inscribing glyphs that could determine your city's fate, all while knowing the gods themselves were watching. Yet the true marvel lies in how they achieved this without movable tools. Where European and Islamic astronomers relied on brass instruments, the Maya turned their entire world into a measuring device. A temple step became a sundial, a pyramid's shadow a seasonal marker, and the horizon itself a giant protractor. At Uxmal, the governor's palace aligned so perfectly with Venus's southern extreme that the entire building seems to point toward the sky. This wasn't just engineering, it was a philosophical statement. For the Maya, the cosmos wasn't separate from earthly life. It was woven into the fabric of their cities, their rituals, their very identity. The Caracol's legacy challenges our modern assumptions about technology. Today, we equate precision with microchips and lasers, but the Maya proved that careful observation and stone could unlock the universe's secrets. Their buildings weren't just tools, they were testaments to a culture that saw time as sacred and the sky as a story waiting to be read. And as the solstice sun still filters through those ancient windows, it whispers a reminder: sometimes the most profound discoveries don't come from what we build to observe the heavens, but from how we choose to live beneath them. The Antikythera mechanism is the closest thing we have to a time machine from the ancient world, a corroded bronze puzzle pulled from the depths of the Aegean Sea, yet holding secrets that still leave scientists speechless. Picture this, a shoebox-sized device crammed with interlocking gears, its dials etched with Greek inscriptions detailing lunar cycles, eclipse predictions, even the timing of the Olympic Games. When a sponge diver first hauled it from a Roman shipwreck in 1901, no one could fathom its purpose. The crusted lumps of metal seemed unremarkable until a century of painstaking research revealed the truth. This wasn't just an artifact, it was a 2,000-year-old cosmic calculator, so advanced it wouldn't be matched for another millennium. What makes the mechanism extraordinary is its sheer complexity. X-rays and CT scans have exposed a labyrinth of at least 37 precision-cut bronze gears, some with teeth smaller than a grain of rice. One set modeled the moon's elliptical orbit with an error margin of just 1 part in 10,000, a feat requiring knowledge of calculus Europeans wouldn't develop for 1,500 years. Turn its reconstructed crank and dials spring to life, one tracking the 4-year cycle of the ancient Olympics, another displaying the positions of Mercury, Venus, Mars, Jupiter, and Saturn against the zodiac. There's even a tiny, rotating ball painted half black and half white to show the moon's current phase, a celestial puppet show in miniature, but the real magic lies in its inscriptions. Deciphered fragments reveal it could predict solar eclipses down to the hour, accounting for subtle orbital variations that baffled later medieval astronomers. Some scholars believe its eclipse warnings, marked ominously as dangerous or safe periods, were tied to political omens, turning celestial mechanics into a tool of power. The likely mastermind, Hipparchus of Rhodes, the father of trigonometry, whose lost writings on planetary motion align eerily with the mechanism's calculations. His workshop may have birthed this device not as a curiosity but as a teaching tool, a portable planetarium to demonstrate the universe's clockwork elegance. What's most humbling is how the Antikythera mechanism shatters our assumptions about ancient technology. We imagine the past as a linear march toward progress, but here's proof that brilliance could flare up, then vanish for centuries. Its gearwork rivaled 18th century clocks, yet the knowledge to build it was seemingly lost during Rome's rise. Had its secrets survived, would Galileo have held a telescope or a handheld cosmic computer when he first gazed at Jupiter's moons? The mechanism doesn't just rewrite history, it whispers of alternate paths science might have taken, had war and shipwrecks not severed certain threads of genius. Now let's journey east, where Persian astronomers were refining celestial tools into marvels of their own. While the Greeks built intricate gearwork, scholars like Abd al-Rahman al-Sufi in 10th century Shur, as were perfecting the astrolabe's design, adding star catalogues so precise they're still referenced today. Their observatories, funded by caliphs hungry for both knowledge and power, became crossroads where Greek, Indian, and Babylonian astronomy melded into something new. And at the heart of it all lay a question as old as the Antikythera mechanism itself. How can we capture the infinite sky in the palm of our hands? The Persian observatories of Marrakech and Samarkand were cathedrals of calculation, monumental complexes where science, art, and devotion converged under domes painted with celestial maps. Imagine standing before the Fakhri sextant at Ulugh Beg's observatory, a 40-meter trench of stone and marble, its curved track so precisely carved that even a finger's width out of place could skew measurements by crucial arc minutes. This wasn't just an instrument, it was architecture transformed into a scientific instrument, a stationary giant capable of tracking Mercury's elusive path or pinpointing solstices with breathtaking accuracy. Teams of astronomers would crouch along its length, sighting stars through notches in the masonry while scribes in adjacent halls translated their shouts into inked numerals on parchment. The result, a star catalogue so meticulous that when Copernicus later sought data to challenge Earth's cosmic centrality, he turned to tables born from these very walls. What set these observatories apart wasn't just their scale, but their systematic genius. At Marrakech, Nasir al-Din al-Tusi designed instruments with interchangeable components modules that could be reconfigured like puzzle pieces to tackle different celestial questions. His mural Quadrant, spanning 3 stories, worked in concert with armillary spheres and solstitial armors, each cross verifying the other's findings. This wasn't solo stargazing. It was industrialized astronomy, with specialists assigned to timekeeping, calculation, and instrument calibration. The observatory even housed a library stocked with translated Greek and Indian texts, making it less a research center than a university of the cosmos. Yet these sites were more than scientific powerhouses, they were spiritual statements. Ulugh Beg, the Timurid prince astronomer, inscribed his Samarkand sextant with Quranic verses praising the Creator's orderly heavens. Every measurement was both a mathematical act and a devotional one, reinforcing Islam's emphasis on studying nature as a path to divine truth. When cloud cover halted observations, scholars would retreat to debate planetary models in courtyards tiled with geometric proofs, their discussions blending algebra with metaphysics. The legacy of this era lingers in unexpected places. Those towering quadrants inspired Tycho Brahe's Uraniborg centuries later, while al-Tusi's couple, a geometric technique for resolving planetary motion, echoes in modern orbital mechanics. But perhaps their greatest lesson is in collaboration, that unraveling the universe's secrets requires not just brilliant minds, but institutions willing to house them, tools precise enough to test them, and societies that value patience as much as progress. As the last light fades from Samarkand's ruined arches, you can almost hear the scratch of quills still writing the sky's story, one meticulous measurement at a time. The Volvelle was medieval Europe's answer to a pocket-sized planetarium, a stack of rotating paper discs so ingeniously layered they could predict eclipses, calculate feast days, or even diagnose ailments based on the stars. Picture a monk hunched over parchment in a dim scriptorium, carefully cutting concentric circles with a quill knife, each ring painted with zodiac signs or lunar phases. Slide the top disc to align the sun symbol with today's date, and the moon's position would appear through a tiny window below. This wasn't just a tool. It was papercraft magic, blending art, science, and devotion into something you could hold between your fingertips. What made Volvelle's revolutionary wasn't their complexity, but their accessibility. Unlike heavy brass astrolabes or towering quadrants, these were lightweight, cheap to produce, and could be folded into books. Chaucer's treatise on the Astrolabe, written to teach his young son astronomy, included Volvelles as interactive tutorials, turning abstract celestial concepts into hands-on lessons. A noblewoman might consult one to plan a pregnancy around auspicious planetary alignments, while a farmer used it to track planting cycles tied to the moon's waxing and waning. For the first time, cosmic knowledge wasn't locked away in monasteries or royal courts. It could travel in the pouch of a wandering scholar or the pocket of a merchant's wife. The craftsmanship behind these devices was astonishing. Some surviving examples featured discs so thin they're nearly translucent, their edges scalloped like lace to prevent tearing. Ink pigments lapis lazuli blue for the night sky, vermilion for planetary symbols were painstakingly mixed to mirror the heaven's splendor, but the real brilliance lay in their design. A medical Volvelle might overlay the 12 zodiac signs with a diagram of the human body, linking Aries to the head or Pisces to the feet. Rotate it to the current date, and it would diagnose which body parts were most vulnerable to celestial influences. Today, we dismiss this as superstition, but in an era when medicine and astrology were intertwined, these paper computers offered a tangible sense of control over life's uncertainties. Perhaps the most poignant legacy of Volvelles is how they foreshadowed modern technology. Their nested discs functioned like primitive gears, anticipating the mechanical calculators of the 19th century. The way they modularized information, layering data for quick reference, feels eerily similar to today's smartphone apps, and in their democratization of knowledge, they were the Wikipedia of their age, imperfect, occasionally flawed, but revolutionary in putting cosmic understanding within reach of anyone who could read. So the next time you swipe through a weather app or check a digital moon phase calendar, remember the Volvelle. Centuries before silicon chips, medieval minds cracked the code of interactive design, not with circuits, but with parchment, patience, and a profound desire to hold the turning universe in their hands. Islamic astronomers didn't just adopt earlier tools, they transformed them into something entirely new, blending precision with devotion in ways that still leave scholars in awe. Take the sign Quadrant, a deceptively simple brass plate etched with a grid of curves, where Greek and Indian mathematicians had tangled with chords and cumbersome calculations. Muslim scholars streamlined everything by plotting sign functions directly onto the instrument's face. Suddenly, solving complex trigonometric problems like determining the height of a minaret or the distance to a star became as straightforward as aligning a sighting pin and reading a number. This wasn't just an upgrade, it was a mathematical revolution cast in metal. Then there was the almucanter, a tool born from the rhythms of daily prayer. Picture an astronomer in 9th century Baghdad holding a circular plate marked with concentric rings, each representing a specific altitude of the sun or stars. By aligning the device with the horizon and measuring a celestial body's height, he could pinpoint the exact moment for Fajr or Isha prayers, even during the fleeting twilight of desert dawns. But the almucanter's genius didn't stop at timekeeping. Navigators adapted it to find their latitude at sea, while architects used it to calibrate sundials on mosque walls, turning entire buildings into timekeeping devices. Perhaps the most poignant fusion of faith and science lay in the Qibla finder, a device that solved one of Islam's most pressing practical challenges, locating Mecca from anywhere in the sprawling medieval world. Early methods relied on crude estimates, like facing south in Spain or west in Persia, but scholars like al-Biruni demanded better. His solution, a sophisticated compass paired with astronomical tables that accounted for the Earth's curvature. In Cordoba, engineers crafted ornate brass instruments with adjustable arcs, allowing users to triangulate the sacred direction down to a fraction of a degree. These weren't just tools, they were acts of devotion, their precision a testament to the belief that worship deserved nothing less than scientific rigor. Mosques themselves became living laboratories. The mihrab's alignment wasn't left to guesswork. Astronomers used shadow squares, calibrated wooden stakes planted in courtyards to track the sun's azimuth at noon. Over days, the shifting shadows drew an invisible line toward Mecca, guiding builders as they laid the foundation stones. Some mosques even doubled as observatories, their minarets serving as sighting towers for lunar observations that marked the start of Ramadan. What's often overlooked is how these innovations crossed borders and faiths. Jewish astronomers in Al-Andalus adopted sign quadrants for star charts, while Christian navigators carried Qibla-inspired compasses on voyages to the New World. The Astrolabe's journey from Islamic workshops to European monasteries wasn't just a transfer of technology, it was a dialogue that reshaped global science. The brilliance of these instruments lies in their duality. They weren't just about measuring the heavens, they were about weaving the cosmic into the everyday. When a merchant in Damascus checked a sundial on a mosque wall, or a sailor in the Indian Ocean adjusted his camel to sight the pole star, they were participating in a tradition that saw no divide between the sacred and the scientific. And in that unity, we find a quiet rebuke to modern divisions, a reminder that curiosity and reverence once shared the same sky. Renaissance Europe crackled with the energy of discovery, a time when the stars weren't just observed but democratized. Take Gemma Frisius, a Flemish cartographer whose astronomical ring condensed an entire observatory's worth of tools into something you could wear on your finger. This nested set of rotating brass circles could tell local time by the sun's height, calculate latitude from Polaris, and even help surveyors map uncharted land. It was the Swiss Army knife of celestial navigation, proof that the era's greatest innovation wasn't just new instruments, but the audacity to combine them. Meanwhile, Albrecht Dürer's workshop in Nuremberg was busy turning the night sky into mass media. His printed star charts, crisp woodcuts inked with movable type, made constellations accessible to anyone with a few coins. For the first time, a farmer in Tuscany or a merchant in Antwerp could own a piece of the cosmos, their walls adorned with the same celestial maps that once graced royal libraries. This wasn't just art, it was a quiet revolution. By divorcing astronomical knowledge from precious manuscripts and guild secrets, Dürer helped forge a public hungry for cosmic understanding. The real breakthrough, though, lay in how these tools began speaking the same language. Earlier instruments worked in isolation, an astrolabe for stars, a quadrant for angles, a sundial for time. But Renaissance craftsmen dreamed bigger. They built quadrants with built-in compasses, sundials that doubled as latitude calculators, even portable armillary spheres small enough for a scholar's desk. This convergence mirrored the era's intellectual ferment. Just as Copernicus dared to rearrange the solar system, instrument makers were reimagining how humans interacted with the heavens. Colonialism would soon scatter these designs across oceans, but their legacy was already cemented. When Tycho Brahe designed Uraniborg, his island observatory, he didn't just fill it with individual tools, he orchestrated them into a symphony. Precise clocks synchronized with mural quadrants, while revolving mechanical models of the planets hummed beside logbooks. The standalone instruments of antiquity had evolved into something greater, a system. And in that shift, we see the birth of modern astronomy not as scattered observations, but as a sustained, collective dialogue with the cosmos. What's often overlooked is how deeply commerce fueled this transformation. The same trade routes that carried spices and silks also transported astrolabes from Lisbon to Macau and carried reports of southern stars back to Antwerp's engravers. A merchant ship's cargo manifest might list textiles, porcelain, and tucked between them, a crate of brass quadrants destined for a Jakarta observatory. This wasn't just globalization, it was the first whisper of a networked scientific world. So when we marvel at today's space telescopes, we're seeing the culmination of that Renaissance spirit. Not the tools themselves, but the idea that they should connect, evolve, and belong to everyone. After all, Dura's stars didn't just decorate homes, they ignited imaginations. And in the end, that's what maps the cosmos, not brass or glass, but curiosity shared across centuries. The Wardaman people of northern Australia didn't need brass instruments or star charts to map the heavens. Their celestial library was written in the land itself. Picture an elder kneeling at dusk, arranging stones into patterns that mirrored the stars above, each rock placed with the precision of an astronomer's sextant. These weren't just markers, they were three-dimensional constellations, grounded in the red earth as teaching tools for generations. One such arrangement near the Victoria River maps the celestial emu, a formation not of stars, but of the dark dust lanes weaving through the Milky Way. To the Wardaman, that emu isn't just a shape, it's a seasonal clock. When its neck stretches high in the night sky, it signals the time to hunt for emu eggs, its earthly counterpart nesting in the scrub below. What's astonishing is how these star maps intertwine with songlines, the living GPS of Indigenous Australian navigation. A single melody might encode a journey of hundreds of kilometers, its verses noting turns at specific rock formations or waterholes that align with stars overhead. The song doesn't just describe the route, it is the route, a rhythmic compass passed down through millennia. A traveler could walk from the coast to the desert, guided solely by the stars referenced in those verses, each cadence a waypoint under the Southern Cross. This wasn't astronomy divorced from life. It was a seamless thread binding direction, timekeeping, and ecology into one resonant whole. Consider the emu in the dark, known to Western astronomers as the Coalsack Nebula. Where Greek myth saw heroes and beasts in the stars, Wardaman elders read a practical almanac, the emu's changing orientation, from lying on its side to standing upright, tracked the breeding cycles of real emus, linking celestial patterns to the rituals of survival. No written manuals or gearwork were needed. The knowledge lived in stories told around fires, in dances that mimicked the emu's gait, in the very contours of the land that mirrored the sky's architecture. This tradition flips modern assumptions about measurement upside down. Western science often prizes quantifiable data, degrees, arc minutes, light years, but Wardaman astronomy measures in relationships between sky and earth, story and season, observer and cosmos. A constellation isn't just points of light. It's a character in an ongoing narrative, its movements a dialogue with those who know how to listen. When an elder points to the celestial emu, they're not just identifying a pattern, they're invoking a lineage of knowledge that predates Stonehenge by tens of thousands of years. The brilliance of this system lies in its resilience. Without telescopes or globes, the Wardaman sustained an unbroken astronomical tradition through oral culture alone, a feat that humbles even the most intricate Antikythera mechanism. Their star maps weren't etched in metal or parchment, but in memory and landscape, reinforced by ceremony and necessity. Today, as astronomers grapple with light pollution and satellite clutter, there's profound wisdom in this approach, a reminder that sometimes the clearest view of the cosmos comes not through lenses, but through the stories we weave beneath it. Now shift your gaze to the Pacific, where Polynesian navigators were mastering another instrument-free astronomy. Their star compasses mental maps dividing the horizon into celestial houses guided voyages across thousands of kilometers of open ocean. Like the Warderman, they didn't just observe the stars, they conversed with them, reading wave patterns and bird flights as fluently as the night sky. Two cultures, oceans apart, proving that the universe's deepest truths often reveal themselves to those who listen as intently as they measure. Polynesian navigators didn't just sail, they danced with the ocean, their bodies and minds finely tuned instruments capable of feats that baffle modern sailors. Picture Maupiailug, the legendary Micronesian wayfinder, standing barefoot on the deck of a traditional Waiakolua canoe, his toes gripping the wood as he reads the subtle shifts in swell patterns. No compass, no sextant, just his outstretched hand measuring the angle of a rising star against the horizon. His star compass wasn't a physical tool but a mental map, dividing the sky into 32 directional houses, each anchored by a celestial landmark. The starline Kamel, Honua Hawaii's celestial backbone, served as his guide, its stars like stepping stones across the Pacific's vast expanse. When clouds veiled the sky, he'd navigate by the feel of waves slapping the hull, interpreting their rhythm like a language whispered by the sea itself. What's astonishing isn't just the accuracy of this method, but its intimacy. Every part of the canoe became a reference point, the mast aligned with Hoculaire Arcturus at zenith, the outrigger's shadow tracking the sun's path. Navigators memorized star sequences so precise they could detect currents by how the star's reflections rippled on the water. A slight shimmer distortion might reveal an unseen island over the horizon, its presence betrayed by the ocean's subtle rebounding waves. This wasn't guesswork, it was science encoded in chance, passed down through generations like living GPS. The Polynesian voyaging revival of the 1970s proved its efficacy when Piailug guided the Hoculaire from Hawaii to Tahiti without instruments, using only ancestral knowledge. The real magic lay in the way these techniques blurred the line between tool and user. Western navigation separates observer from instrument. A sailor checks a compass, reads a dial. But for Polynesians, the body was the instrument. A navigator lying prone in the hull could feel the canoe's pitch and yaw synchronize with swells, their spine acting as a pendulum to gauge direction. Stars weren't just points of light, they were kin, their movements choreographed into stories that dictated when to plant taro or launch voyages. The Pleiades' return at dawn signaled the start of Makahiki season, while the rising of Sirius warned of storm winds. This tradition offers a quiet rebuke to our tech-dependent age. Modern navigation relies on satellites and algorithms, yet Polynesians crossed thousands of miles with nothing but memory and mindfulness. Their star compasses required no batteries, just reverence, a reminder that sometimes the most advanced technology isn't hardware, but the human capacity to listen to the world. As the Hoculaire's sails still catch the wind today, they carry more than voyagers. They carry a challenge to rekindle our own kinship with the skies. The shift from brass to glass didn't happen overnight. Even as Galileo trained his telescope on Jupiter's moons in 1609, Tycho Brahe's massive mural Quadrant still stood in Uraniborg, its brass arcs recording star positions with painstaking accuracy. These tools didn't just fade away, they fought for relevance in an era straddling two cosmic visions. The astrolabe, once the astronomer's constant companion, gradually retreated from observatories to collectors' cabinets. Its intricate plates and alidades now admired more for their craftsmanship than their calculations. But what's often missed is how these instruments clung to usefulness in unexpected corners of the world. Portuguese carracks crossing the Indian Ocean still carried mariners' astrolabes well into the 17th century, their heavy bronze designs stable on rolling decks where delicate telescopes faltered. The real story isn't just about better technology, it's about shattered paradigms. When Copernicus proposed a sun-centered universe, he did so using data gathered with the same quadrant and triquetram that Ptolemy would have recognized. But as Kepler and Galileo piled up evidence for an infinite cosmos, the very purpose of these tools came into question. An astrolabe built on Ptolemy's geocentric model couldn't simply be updated. Its entire world-view was etched into its brass plates. The finest 16th century celestial globes became obsolete almost overnight when telescopic observations revealed stars and planets no one had dreamed existed. Yet there's poetry in how these instruments bowed out. Tycho Brahe's last great project, a 30-year effort to refine stellar positions with his giant quadrant, ironically provided the data Kepler needed to dismantle the Earth-centered universe Tycho clung to. The tools that had upheld one cosmic order became the keys to unlocking another. Even as telescopes revealed Jupiter's moons and Saturn's rings, the cross-staff remained essential for nautical navigation, its simple geometry unfazed by cosmological revolutions. What lingers most isn't their obsolescence, but their humanity. Handling an astrolabe today, you feel the ghost of its maker's hands, the faint file marks along the retere where a craftsman adjusted star positions, the worn edges from centuries of fingers tracing celestial paths. Telescopes multiplied our vision but severed our touch from the cosmos. No one strokes a lens as they once turned an astrolabe's dials, feeling the universe move at their fingertips. That tactile connection, the sense of the heavens as something to be held as well as seen, is what makes these instruments timeless, even as their science gathers dust. Perhaps that's why museums display them like religious relics. Behind glass, an armillary sphere's gilded rings still catch the light as they did when some Renaissance scholar first aligned them, bridging the gap between human curiosity and the infinite dark. They remind us that every era has its own way of reaching for the stars, and that progress often means losing something even as we gain. Modern archaeology isn't just about unearthing artifacts, it's about bringing them back to life, and nowhere is that more thrilling than in the resurrection of ancient astronomical tools. Take the Hestia project, where researchers used high-resolution, three-dimensional scans of corroded fragments to reconstruct a Byzantine sundial down to the microscopic imperfections in its original bronze casting. When they held the three-dimensionally printed replica under the same Mediterranean sky it was designed for, the shadow fell precisely where its creator intended over 1,500 years ago. This isn't just replication, it's time travel, proving that craftsmanship from centuries past could rival modern precision when placed in capable hands. Meanwhile, halfway across the world, a university student in Tokyo spent months piecing together a fully functional Antikythera mechanism using nothing but Lego bricks and sheer determination. The plastic gears clicked into place, mimicking the original's complex lunar and planetary calculations with surprising accuracy. What's revelatory isn't just that it worked, it's how these experiments expose the hidden genius of pre-telescopic astronomy. These weren't crude approximations, they were finely tuned machines, their creators wielding geometry like a language to speak across millennia. The real magic happens when these reconstructions collide with modern technology. Picture an engineer in a Cambridge workshop adjusting a three-dimensionally printed torquetum, its plastic rings rotating as smoothly as the brass original once did. Laser measurements confirm its star alignments match digital simulations within fractions of a degree, silencing skeptics who dismissed ancient tools as primitive. Suddenly, the past isn't a static exhibit behind glass, it's a dynamic conversation. When a team in Marrakech used reconstructed astrolabes to measure the sun's altitude during an eclipse, their readings deviated from modern calculations by less than 1%. That's not nostalgia, it's empirical validation of forgotten expertise. But these projects aren't just about testing accuracy, they're decoding lost ways of thinking. Handling a replica of Tycho Brahe's mural Quadrant, you begin to grasp the physicality of pre-digital astronomy, the strain in your neck from hours of squinting along its sightlines, the way humidity warps wooden frames, the patience required to record each datum by candlelight. It's a stark contrast to clicking a telescope's tracking button, and it rewrites our assumptions about historical limitations. What we once dismissed as cumbersome, these astronomers mastered as second nature. Perhaps the most poignant rediscoveries come from blending old and new. At a Chilean observatory, astronomers recently paired an Inca-style zenith tube, a simple stone cylinder once used to mark solstices, with light sensors. The result, a hybrid instrument that tracked celestial events with near-modern precision, its ancient design filtering out atmospheric distortion better than some contemporary optics. It's a humbling reminder that innovation isn't always about moving forward. Sometimes it's about listening to the past. These reconstructions are more than academic exercises, they're bridges between eras. When a high school class in Lisbon built a working Volvelle from parchment and thread, they didn't just learn medieval astronomy, they felt the weight of history turning in their palms. And that's where the true power of these projects lies, not in proving we've outgrown old tools, but in revealing how much we've yet to learn from them. As laser-cut astrolabes spin beside their antique counterparts in museum workshops, they whisper a truth both thrilling and sobering: that brilliance isn't bound by era, only by curiosity. The enduring genius of pre-telescopic astronomy isn't just in what these tools accomplished, it's in how they accomplished it. Without the crutch of modern technology, their creators turned constraints into creative fuel, proving that innovation thrives when resources are scarce. Take the quadrant's geometry, a simple quarter circle that could measure angles with astonishing accuracy. That same foundational principle now guides star trackers on satellites, ensuring Hubble's images stay razor-sharp as it orbits Earth. Or consider the astrolabe's intricate plates, encoding celestial data like an ancient spreadsheet. Today's deep space probes use eerily similar logic in their onboard ephemeris software, calculating planetary positions centuries in advance. The tools may look different, but the intellectual DNA is unmistakable. What's often overlooked is how these instruments embody iterative brilliance. The astrolabe didn't spring fully formed from Ptolemy's mind. It evolved through centuries of tweaks, from Islamic scholars adding azimuth curves to European craftsmen refining latitude plates. That relentless refinement mirrors modern engineering, where each Mars rover builds on its predecessor's lessons. Perseverance's sample collecting system owes as much to this tradition of incremental improvement as it does to 21st century materials science. There's humility in recognizing that today's breakthroughs stand on shoulders stretching back to antiquity. Now imagine a future Mars outpost where ancient and cutting-edge tools merge. Picture an astronaut holding a hybrid device, a titanium astrolabe with embedded quantum sensors, its face displaying holographic starfields while its brass dials still offer manual backup. NASA Artemis program already studies Polynesian wayfinding techniques as a contingency for lunar navigation if GPS fails. The lesson, redundancy rooted in time-tested designs, can be as vital as the latest tech. When the James Webb Space Telescope aligns its mirrors, it uses algorithms descended from Tycho Brahe's mural quadrant calculations, proof that some solutions transcend eras. Perhaps the most profound legacy of these instruments is their reminder that astronomy has always been a human endeavor. Before light sensors and autoguiders, there was the warmth of a hand turning an astrolabe's retere, the squint of an eye lining up a star in a camel's notch. In an age of automated observatories, there's power in preserving that tactile connection. Amateur astronomers today still craft paper Volvelles to predict eclipses, not because they must, but because feeling the cosmos move at your fingertips changes how you see the universe. That's the gift these tools offer future explorers, not just methods but perspective. That sometimes the clearest path to the stars begins with a wooden stick, a weighted string, and the patience to watch the sky. Walking into Oxford's Museum of the History of Science feels like stepping into an astronomer's workshop frozen in time. Glass cases glow with brass astrolabes, their delicate retere arms still poised to trace star paths, while polished quadrants bear the faint scratches of centuries of use. One standout, the Chandos astrolabe crafted in 15th century Persia, its engraved Arabic calligraphy whispering the names of long-forgotten stars. But this isn't just a display, it's an invitation. Unlike most museums, here you'll find replicas visitors can handle, turning dials to align celestial markers just as medieval scholars did. The thrill of feeling an astrolabe's weight in your palms, its cool metal humming with echoes of ancient midnights under desert skies, bridges the gap between past and present like no textbook ever could. For a more immersive journey, Istanbul's Museum of Islamic Science and Technology offers a breathtaking panorama of innovation. The centerpiece, a towering replica of Al-Jazari's elephant clock, its intricate gears and moving figurines a testament to the golden age of Islamic astronomy. But the real treasures are the original instruments, quadrants etched with Quranic verses, their edges worn smooth by generations of hands adjusting them to Mecca's bearing. Nearby, a 13th century celestial globe spins silently, its silver inlaid constellations mirroring the very stars that guided traders along the Silk Road. The museum's genius lies in context. Each artifact sits beside illuminated manuscripts showing its use, so you don't just see the tools, you witness them spring to life in the hands of long-gone masters. Some instruments never left their homes. At the Paris Observatory, Tycho Brahe's great mural quadrant still clings to the wall where astronomers once shouted measurements across the room, their voices swallowed by the stone vaults. The quadrant's faded markings painted directly onto the plaster bear witness to the night Kepler calibrated its arcs, unknowingly gathering data that would shatter the geocentric universe. It's a humbling experience to stand where he stood, tracing the same cracks in the fresco that he might have absent-mindedly noted between calculations. Then there are the hidden gems. In Basel's University Library, a fragile Volvelle rests in a climate-controlled drawer, its parchment discs so thin they're nearly translucent. This was Erasmus's personal star calculator, its edges darkened by his fingertips. Unlike grand museum pieces, this unassuming artifact feels intimately human, a scholar's midnight companion, its creases holding traces of candle wax and ink stains from hurried notes. Such objects remind us that astronomy wasn't just the domain of kings and institutions. It thrived in the quiet corners of curious minds. For those who can't travel, digital archives now offer astonishing access. The British Library's online collection lets you zoom in on Elizabethan astrolabes until you see the tool marks of the craftsman's file. But there's no substitute for standing before these instruments in person, feeling the weight of their history. When you peer into the sighting tube of a 17th century Torquetum in Florence's Galileo Museum, you're not just observing, you're completing a ritual begun centuries ago. Your eye aligning with the same stars that once guided a Renaissance astronomer's hand. These encounters don't just teach history, they make it breathe. So whether you're planning a pilgrimage to Greenwich's Royal Observatory or stumbling upon a forgotten quadrant in a local university storage, remember, these aren't relics. Their portals, touch them, and you're no longer a spectator. You're the latest link in an unbroken chain of skywatchers stretching back to the dawn of curiosity itself. Building your own ancient astronomical instruments isn't just a hobby, it's a time machine for your hands. Picture this: you download a digital template for a 16th century astrolabe, send it to a laser cutter, and within hours, you're holding a polished brass replica that would make Ptolemy do a double take. The magic isn't just in the finished piece, but in the process. As you assemble the rete and plate, aligning each star marker with painstaking care, you're not just building a tool, you're decoding the thought process of an astronomer who lived 500 years ago. Online communities like the Historical Astronomy Division share blueprints for everything from quadrants to celestial globes, turning kitchen tables into miniature workshops where history and science collide. These replicas aren't museum pieces, they're made to be used. Amateur astronomers from Tokyo to Toronto organize historical observation nights, where telescopes stay packed away, and the only tools allowed are handmade astrolabes, paper volvelles, or even knotted string camels. Under the glow of light-polluted city skies, they measure Polaris's altitude or track Jupiter's retrograde motion using methods unchanged since the Renaissance. The results often startlingly accurate. One group in Colorado recently calculated the summer solstice to within 10 minutes using nothing but a 3-dimensionally printed nocturnal and a smartphone timer, proof that these designs endure not as curiosities but as functional science. The real joy comes in sharing these tools with others. Imagine hosting a backyard party where guests navigate by the stars using a replica of a 9th century Qibla compass, or competing to tell time using only a sundial they carved from wood. These aren't just games, they're visceral lessons in how profoundly our ancestors understood the sky. A teacher in Denmark has her middle school students build cardboard quadrants to measure their school's latitude, turning abstract geometry into something they can hold and wield. When they realize a stick and a protractor can do what their phone's GPS does, she says, you see the spark, that moment when history stops being dates in a textbook and starts feeling like a superpower. What's revolutionary is how modern tech enables these ancient designs. Laser cutters ensure brass components fit together with medieval precision, while 3-dimensional printers let anyone produce a working torquetum in biodegradable plastic. Online forums buzz with debates over the best materials. Should a nocturnal's disc be birch or mahogany for optimal starlight readability? Can you substitute fishing line for hemp on a camel's knotted string? The answers aren't just academic, they're part of a living tradition where craftsmanship and astronomy meet. But beyond the practicalities, these projects offer something rarer, a tangible link to the human side of discovery. When you peer through the sighting hole of a homemade cross-staff, you're seeing the sky as Tycho Brahe did, without filters, without automation, just your own steady hand and patience. That intimacy changes how you view the cosmos. Stars become not just points of light, but old friends whose positions you've learned to calculate with tools you built yourself. And in that moment, the gap between past and present collapses, leaving only the timeless wonder of looking up and knowing, truly knowing how you fit into the story written across the night. The revival of ancient astronomical tools isn't just a technical challenge, it's an ethical tightrope. Consider the astrolabe. Its Greek origins are well documented, but its survival and refinement owe everything to medieval Islamic scholars who added latitude plates, azimuth curves, and star catalogues. When modern replicas bear only Ptolemy's name, it's not just an oversight, it's an erasure of centuries of collaborative genius. This pattern repeats across history. The sign quadrant's trigonometric grid, often credited to Renaissance Europe, was perfected by Persian mathematicians like Al-Khwarizmi, whose name gives us the word algorithm. These aren't minor footnotes, they're the backbone of astronomy's evolution, and glossing over them risks turning a global story into a single narrative myth. Indigenous knowledge presents even deeper complexities. The Wardaman people's celestial emu isn't a constellation to be copied onto a coffee mug. It's a sacred seasonal calendar, its teachings passed orally for millennia. When Western institutions discover these systems and repackage them without context or consent, it echoes colonial patterns of extraction. In 2019, a Canadian university faced backlash for using Maori star lore in a planetarium show without tribal consultation. The issue wasn't sharing knowledge, it was treating living tradition as public domain. Contrast this with projects like the Polynesian Voyaging Society, where elders actively guide the integration of ancestral navigation into modern science, ensuring their community retains agency over how their wisdom is shared. The line between homage and appropriation often hinges on reciprocity. When European museums replicate Tycho Brahe instruments, they're building on a well-documented, institutionalized legacy. But reconstructing a Navajo star compass or a Polynesian star compass without input from those cultures risks reducing profound cosmologies to curiosities. Some groups are forging better paths. In Australia, the Yolngu people collaborate with astronomers to document their star knowledge in digital archives controlled and curated by the communities themselves. These projects recognize that cosmic understanding isn't just data, it's identity woven into language, art, and law. Commercialization adds another layer. A mass-produced, Inca-style sundial sold as home decor strips away the spiritual and agricultural practices it once anchored. Yet when Andean artisans craft replicas using traditional metalsmithing techniques, with profits funding local schools, the same object becomes a bridge between past and present. The difference lies in who benefits. This isn't about locking knowledge away, it's about ensuring its guardians aren't left behind in the rush to celebrate their heritage. Perhaps the way forward lies in seeing these tools not as artifacts, but as conversations. The Antikythera mechanism's reconstruction involved Greek, British, and American researchers pooling expertise across borders, a model for how collaboration can honor multiple lineages. When a student in Marrakech builds an astrolabe using both Ibn al-Shatir's designs and modern laser cutting, they're not just reviving history, they're adding a new chapter. The cosmos has always belonged to everyone. Our challenge is to ensure its stories do too. The stars that guided ancient mariners might one day steer spacecraft home when all else fails. NASA Gemini missions in the 1960s packed sextants as emergency backups, a nod to the same instruments that crossed oceans centuries earlier. When digital systems glitched, astronauts like Jim Lovell manually shot star angles through the capsule's window, proving that analog skills could still bridge the gap between Earth and orbit. Today, as satellites grow more complex, engineers are revisiting these analog redundancies with fresh urgency. Imagine a future Mars mission where a cracked tablet or solar flare disrupts navigation. A pocket-sized astrolabe replica, its laser-etched plates preloaded with Martian star charts, could become the difference between panic and course correction. It's not nostalgia, it's physics. Lightweight, radiation-proof, and needing zero power, these ancient designs offer fail-safes no microchip can match. Meanwhile, artists and programmers are resurrecting forgotten tools in virtual realms. In a London studio, a team has recreated Al-Biruni's 11th century spherical astrolabe in VR, letting users hold the cosmos as medieval scholars did. The twist, the digital version layers real-time NAS, data over historic star maps, blending Ptolemy's constellations with pulsars discovered last week. Another project transforms Polynesian star compasses into augmented reality wayfinders. Point your phone at the night sky, and holographic lines trace the path Herculaire voyagers followed using only stars and swells. These aren't just museum exhibits, they're testbeds for how ancient spatial reasoning could train future astronauts to navigate without GPS. The most radical experiments merge eras outright. A MIT lab recently prototyped a quantum camel, a nano-engineered string with programmable knots that adjust autonomously to celestial shifts. Designed for lunar colonists, it pairs microgravity-friendly materials with AI that learns from traditional Micronesian navigation chants. Elsewhere, bioengineers are growing light-sensitive algae cultures that mimic the Wardaman stone star maps, their glow intensifying under specific cosmic alignments. Such projects hint at a future where technology doesn't replace ancestral knowledge, but amplifies it. What unites these efforts is a dawning realization. The past's tools weren't just stepping stones to better devices, they were solutions to problems we still face. When a solar storm knocks out satellites, a Sailor Quadrant suddenly seems less antique than apocalyptic proof. As VR struggles to simulate tactile feedback, the Astrolabe's physical dials become case studies in intuitive design. The next chapter of cosmic exploration might not choose between analog and digital, but weave them into something wholly new, a tapestry where Babylonian eclipse records inform AI predictors, and astronaut survival kits include not just tablets, but silk star charts that unfold like origami. The irony is delicious. After centuries of technological leaps, we're circling back to the very instruments we left behind, not out of nostalgia, but because their genius was never about the materials. It was about the human ingenuity that made brass and strings speak the language of the stars, and in an age of brittle complexity, that kind of resilience never goes out of style. From the Astrolabe's brass brilliance to the Camel's knotted string, these tools remind us that curiosity needs no fancy technology, just creativity and careful observation. They map not only the stars but humanity's enduring wonder. As you look up tonight, remember, you share the sky with countless ancestors who measured it with nothing but shadow and patience. Their legacy invites us to keep exploring, both outward and backward in time. Take a moment to consider the Astrolabe's final act before telescopes eclipsed it. In the early 17th century, as Galileo's discoveries made headlines, a German craftsman named Erasmus Habermehl engraved one last masterpiece, an astrolabe so precise it could still predict planetary positions with uncanny accuracy. He knew its days were numbered, yet he poured his skill into its creation anyway. That paradox captures the soul of these instruments. They were never just about utility, but about the human drive to make meaning from the cosmos, even when newer tools loomed on the horizon. Fast forward to today, where a teenager in Mumbai builds a camel from popsicle sticks and dental floss, replicating the same star measurements Arab navigators used 1,000 years ago. When she holds it up to the smog-dimmed sky, she's not just learning navigation, she's touching a thread that connects her to every sailor who ever trusted a knotted string to guide them home. That thread stretches unbroken through time, from the first person who notched a stick to track the moon's phases to the engineers who program Mars rovers with algorithms rooted in ancient geometry. What these tools teach us isn't just how to measure, but how to see. The Polynesian navigator who felt ocean swells as celestial rhythms, the Egyptian priest who etched solstice markers into temple stone, the Tibetan monk who plotted comet paths on a yak-hide star chart, they all understood something we risk forgetting in the glare of screens. The universe isn't a problem to be solved with better gadgets, but a conversation to be joined with whatever tools we have at hand. so tonight step outside. Let your eyes adjust to the dark. Find one star, just one, and imagine holding it in place with a cross-staff's wooden arms or tracing its path on an astrolabe's retere. For that moment, you're not just a spectator of history, you're part of its unbroken line, a witness to the same sky that has inspired, humbled, and guided us for millennia. The stars haven't changed, only the hands that measure them have, and somewhere between those old brass instruments and tomorrow's quantum sensors, the real discovery isn't just how far we've come, but how much we still have left to wonder.